A few words about the roundtable that will happen after the coffee break this afternoon. So this roundtable is basically an opportunity for you to ask questions to all of the speakers, the organizers too, or each other if you want, about everything but the contents of the lectures, essentially. Or if we run out of such questions, maybe about the contents of the lectures. But how life is in academia, what's careers, what is it how is it to be a professor, how you arrived there, trajectories, choices, bifurcations, trade-offs. Think about it, prepare your questions, and we'll have hopefully a nice discussion. Do you want to add something? Okay, so Nigel.
Okay. Okay, so today we're going to work on quasi-cycles, how you get persistent population cycles. We're going to work that out analytically. We're going to finish what we were discussing last time. And then I'm going to show you the theory for stochastic Turing patterns. And tomorrow, I'm going to explain to you, not on the blackboard, but with slides, about brain waves. So pattern formation in the brain, in your brain right now as it happens. And then I'm going to give you about the hands-on, the class project. And so I'm going to tell you a little bit about what the idea is. It'll be done next week. No, I won't be here. In fact, many of the people, well, we'll explain it tomorrow, but there's a very interesting and exciting class project that we've devised for you that will reflect some of the science that we've been talking about in these lectures. Come on in. Have a seat, have a seat, have a seat. Roll up, roll up. Okay, so yesterday we discussed how to make an individual level model for predator-prey. We discussed various ways to approach it analytically, and I showed you that we're going to try a systematic expansion of the individual level model. We're going to split the dynamics into an expansion where the zeroth order is going to be the deterministic part. The first order will turn out to be the lowest order contribution to the stochastic part. And the way we're going to do this is we're going to write that the individual numbers of predators and prey, predator is A, prey is B, we will write as the density, phi I, which is Ni over V, so this is the density times the volume, and then there's a correction term which scales with the volume, the square root of that, times something which is a random variable which is fluctuating, and we'll actually compute what is the statistics of this fluctuating variable. So that's the setup. That's where we finished last time. So the next step that we want to do is we need to take the master equation that we had written down, and by now you should be familiar with the concept. Take the master equation and use that to derive the dynamical equation for the probability distribution of the fluctuations. Okay, so the way we're going to do that is we take our master equation, which I'm not going to waste time by writing it down, and then we're going to expand in powers of v to the minus a half. V is our volume where the particles reside, but in reality it's a correlation volume, and we'll talk about that later. And so what we're going to write down is that P of the particles N and T, the number of prey, the number of predators, we're going to write that as some new function, which we'll call pi, which will be a function of the fluctuations in the predators, the fluctuations in the prey, and then the master equation will turn out to be this. So it's equal to d pi by dt. And then now what we do is we use the chain rule, and what we end up with is this. So this is the governing equation for P. That's the master equation, and phi here. These phi are the lowest order mean field solutions. We'll get an equation for them, and these things will turn out to be to obey the Lotka-Volterra equations. So we're going to see that in just a minute. And then from that, we will be able to get a closed equation for the fluctuations. So now, if you remember, when we wrote down this master equation, I wrote it down in terms of what I called ladder operators or step operators, which were operators that added one particle to the predators or subtracted one particle from the predators, or added one particle to the prey or subtracted a particle from the prey. So now we have to write down what are the step operators. So I had two step operators, the plus and minus, and those can be expanded in the following way. And higher order terms like that. And so what we're going to do is we're going to take these expansions, that one and this one, and substitute it into the master equation, and then equate orders in V. So the strategy is substitute into the master equation, and then examine order by order in our expansion parameter, which is going to be the square root of V. So let me write down what you get at order square root of V. So at order square root of V, the equation you end up with is this one. So phi A is the density of predators, phi B is the density of prey. So these are the variables that we actually were using when we wrote down the Lotka-Volterra that you've been using all along. And we've now derived the Lotka-Volterra equations from our individual level model. So this lowest order here is the predation term, phi A, phi B. This is the predator eats the prey. This is the death of the predator. Then the density of the prey, it grows with a logistic growth like this, with C and B being coefficients from the individual level model, and then the predation, and then lastly the death of the predators. Sorry, the death of the prey. And so the birth minus the death of the prey, they sort of come in here at this first order, here, like that. So what we think of as the growth rate is the difference between the birth rate and the death rate. So this is fantastic. So starting from our individual level model, we derived the Lotka-Volterra equations. Okay, so that's nice. So now we go to the next order. So the next order is order V. We go up. Oh, okay, all right. Then come forward. I try not to use blue.
A short question, these chi variables for the P are the same as the ones that appear in the definition of n sub I?
These psi are the same as these psi. Is that what you're asking?
Yeah, yeah.
Yes, that's why they've got the same symbol.
Okay, okay, but okay.
Okay, so I do not advise you to try to check my algebra in real time, because first of all, you won't be able to do it, and second of all, I may make a typo when I write it up on the blackboard. But you will get my notes. So, but is there a question that you have, a conceptual question you're not understanding?
So all we have done here is instead of writing, I guess, yeah, instead of writing an occupation probability distribution, we are writing a probability functional, which is a function of the noise process, which is the only thing that changes from realization to realization, I guess.
Yes, my original master equation is a function of these things. Yeah. And now I'm going to make this change of variables, and then I'm going to end up with a master equation. Once these things have come out, I'm going to get an equation for these psi, and that's the thing that comes in here, and that's the thing I'm going to calculate. And so then I've expanded what the master equation is, the same way that I've expanded the definition of the ends, so that's like this. And then all I've done is substitute those into the big master equation I wrote down last time, and then I didn't show you the algebra. I then just said, let's look at the terms of order square root of v, let's look at the terms of order v naught, and so on and so forth. Okay? Did I answer your question?
Yes.
Yep, okie doke. All right, so then the next term.
So just a minor question.
Go ahead.
In the equation for dp by dt, the pi, is it the pi evaluated at zero noise, or and the last equation there?
Nope, it's pi as a function of the noise. We're going to see. I'm going to write it down for you in just a second. Okay? I'm going to literally write it down. Okay, so the next order term is order v to the 0. So now I calculate the terms for that, and so what I get is d pi by dt as a function of psi and t. So that equals minus sum over I and j equal a and b. aij d by d psi I, psi j pi plus 1/2 sum over I and j b ij d2 pi by d psi I d psi j. And if I write with this blue, is that visible? This blue is visible, but the thin one isn't. Is that the idea? Okay, got it. Thanks for letting me know. Okay, and then so you do that calculation, and then you find that there's two matrices, A and B, and now I will write for you what those matrices are. So A11 is minus dA plus P phi B. A12 equals P phi A. A21 is minus P phi B. And A22 is equal to B minus the death rate of the prey minus P phi A minus C phi B squared. So those are the coefficients. And when I write down A, I, J, where I equals 1, that means A, the predators. And when I write down J is equal to 2, let's say, that means the prey. So I've just written them down like that. And then the matrix B is equal to, why don't I just write it down as a matrix, dA phi A plus P phi A phi B, and then here minus P phi A phi B, here minus P phi A phi B, and then here some awful mess, B phi B plus dB phi B plus P phi A phi B plus C phi B squared, and so that's what you get. Okay, so some awful mess, but everything is calculated. Okay, nothing is guessed. It's all just calculated from the equation, and what you can see is happening. These matrices, this A matrix, and this A matrix here, and the B matrix, they enter into the equations for the psi, for the fluctuations. So there's pi, so the probability distribution of the fluctuations depends on these matrices A and B, and the matrices A and B, they both depend on the previous order in perturbation theory. i.e. phi A and phi B. So you have to first of all solve the lowest order to get phi A and phi B. Then, once you know those things, those are just things that go into the matrices A and B, that determines the fluctuations. So this is like some sort of expansion, a closure expansion in some sense, but this one is very systematic, unlike a closure expansion. And so the fluctuations are determined by the mean field solution. What it means is you first find the mean field theory, and then just like you do in statistical mechanics, you look at the fluctuations of the thermodynamic variables around the mean average values. And that's exactly what we're doing here, but we're doing this dynamically in a stochastic model of predator-prey equations. Okay, now, on the first day or so, I showed you how there is a connection between a Langevin equation and a Fokker-Planck equation. These equations are equations for the probability distribution, and they come from the master equation. But then we also said, well, we can write these things down as a Langevin equation, an equation for the actual variables themselves with some random noises on the right-hand side. So the next thing that I want to show you is what do we get if we try to write down the Langevin equations. So these are Fokker-Planck equations for the probability density of fluctuations. But we're going to get more insight by looking at the Langevin equation. More mechanistic insight. So I showed you what the relationship is between them. I don't expect you to remember it, but it's there. So let me just remind you what we discovered. What we discovered was that if I have a Fokker-Planck equation like this, it comes from a Langevin equation that looks like this. So it's dxi by dt is equal to A times psi, which is a perfectly deterministic equation. And then there is a noise, which I'm going to call gamma of t. So this is going to be my noise. Remember, I talked about the noise coming from a bucket or a box of noisy functions, and we just stick those noisy functions on the right-hand side of our differential equation solver. So this is the noise. This is the deterministic part. And the probability distribution of the gamma is equal to 0, and the second moment, the correlator of the noise between two different components at t and t prime is equal to b I delta of t minus t prime. So this says, take the noise corresponding to, say, the predators with itself, or the noise of predators with the prey, then at different times, t and t prime, they're delta correlated, and how the different components of the noise, one for the predator, one for the prey, they're related by this matrix B that we've just calculated up here. And again, there's no assumptions here. I'm not saying, oh, this is a Gaussian, so I'm just going to put in some width or something like this. This is derived systematically from the individual level model equations. Okay, now this equation also, because this B depends upon the previous order in perturbation theory, it depends on the mean field, so this noise is multiplicative noise. It's multiplicative in the sense that the equation of motion for the fluctuations depends on the solutions to the equations for the mean field. And if I hadn't written down this systematic expansion, I had done what I told you was called the Kramers-Moyal expansion, a different expansion, which is not systematic, I would have derived actually these equations. But those equations, the variable on the left-hand side and the variable that comes in here would have been the same. So, so these things are multiplicative noise. In other words, the noise strength, it's called multiplicative noise because the strength of the noise depends on the solution of the equation. So it's not just adding noise and the coefficient is just KT or something like that. Okay, so now I want to show you, so this equation actually has a very interesting structure, very easy to understand. So without doing too much hard work, let me show you how we interpret what this equation is telling us. So this section is the most important section, the mechanism for persistent cycles. Is my chalk bright enough in the back? Okay, and are there any ecologists in the room who've zoned out because of the equations? Okay, so Johan, this is the bit that actually matters. Okay, so just for the next 5 minutes. Okay. You can keep it open, but this is the bit I want you to hear. Okay, so now we've got this equation. So what I'm going to show you now is that point number one. If I look at this equation for the fluctuations around the average, I don't like this chalk. If I look at the equation for the fluctuations around the average, let's suppose I throw the noise away. So it just looks like this. This equation, you would say, oh, I know how to solve that equation. I just have to look at the eigenvalues of this matrix A, and that will tell me what happens as time goes to infinity. And in fact, the eigenvalues turn out, when you diagonalize this matrix, turn out to be negative, at least negative real parts. And so that means that the Lotka-Volterra solutions are stable fixed points, which we already knew from just looking at the Lotka-Volterra equations themselves. But now when we add the noise, that noise comes in by adding to this deterministic part over here. So there's the deterministic part. What does the noise do? What the noise does, it drives the solutions away from the exponential decay. Okay, so that's just really telling you something that's really just restating what the equation is. But now let's compute something. So what we're going to compute, we're going to assume that the system is in a steady state. And if it's in a steady state, I can solve this equation by writing down a Fourier transform in time. So let's Fourier transform. So the Fourier transform will give me minus I omega, the Fourier transform of the fluctuations as a function of omega, is equal to this matrix A, the Fourier transform psi, plus the Fourier transform of the noise. So that's just Fourier transforming that equation. And the Fourier transform of the noise satisfies this is equal to Bij. So Bij is just a matrix of numbers. Aij is just a matrix of numbers. Those numbers are determined by the zeroth order solutions, the solutions of the Lotka-Volterra equations. And we know that those solutions are just points. They're not oscillations. They're not cycles. Okay, now what I'm going to do is I'm going to compute. I'm going to ask what is the behavior of the solution. And I could look at that by just doing a computer simulation. But a more interesting thing to do is to compute the power spectrum. So what's going to happen is I've got an equation which has noise, it has a steady state solution plus noise, so the solution is going to be flopping around like this. So what I'm going to ask is what is the energy inside each mode of frequency omega. So what we're going to do is compute the power spectrum. To find the energy modes of frequency omega. So the power spectrum, I can define a variety of power spectrums, but they're all basically like this. I take the variable psi I of omega. I take the variable psi j of minus omega, the Fourier transform variable, and I compute that correlation function. The reason there's a minus omega here is because really this would be the complex conjugate of this, because the fluctuations are real variables. If they're real variables, then the complex conjugate of the Fourier transform is the variable in the minus with minus omega rather than plus omega. So then if I then now go ahead and compute that, here's what I get. Let me look at P11, which is the power spectrum of the predators. It looks like this: alpha plus beta omega squared over omega squared minus some number, big omega squared, plus gamma squared omega squared. So that's the calculation you get just by simply taking this algebraic equation, multiplying it by its complex conjugate, and then computing this thing. And so that's what it looks like. And let me tell you what these variables are. So in this equation over here, so alpha is B11 A22 squared plus B22 A12 squared, and beta is equal to B11 just itself, and then omega squared is equal to 2P squared phi A phi B, and gamma is equal to minus A11 minus A22. Okay. How many people here, so those are numbers, all of these constants in here, we've calculated them. Then there's no uncertainty, there's no guesswork. Has anybody here seen a power spectrum like this before? Okay, nobody's shouting out, but let me perhaps put it into a form that is more familiar to you. So,
it seems they're on forced harmonic oscillator.
Brilliant. Forced harmonic oscillator.
Yeah.
It's a forced and damped harmonic oscillator. You're absolutely right. Thank you. Okay, so let's first of all interpret these terms. So you can see here, let's suppose that gamma was equal to 0, all right? So what would happen if gamma was equal to 0 and little omega was equal to this big omega? Then this whole thing would be 0 in the denominator, and the power spectrum would be resuming up to infinity. So this would describe a resonance. It would say that I'm taking an oscillator and I'm forcing it at some frequency. We'll see how it happens. And there's a kind of resonance that happens when omega, the thing that you're looking for, you're looking at what is the frequency we're looking at. When it's equal to this big omega, then there's a huge amount of power that is being spent in that particular mode. Okay? What this gamma does is it damps that. This gamma is damping. And we're going to look a little bit more closely at that. So let me show you why it would be like that. So yes, this describes two coupled, damped, forced harmonic oscillators. Okay, so let's see that. So let's suppose I have two variables. So let's suppose I've got x of t and y of t, and they obey the following equation. X dot is equal to a11x plus a12y plus some gamma 1 of t, and y dot equals a21x plus a22y plus gamma 2 of t. Okay, so I've got two simultaneous first-order differential equations. And I'm going to show you that you can make those, roughly speaking, into one second-order damped differential equation. So so what is the strategy? The strategy is eliminate y. I could eliminate x, but let's just choose to eliminate y of t. So how would we do that? Well, what we do is we can take the x equation and differentiate. So if I differentiate this, then what I get is x double dot equals a11 x dot plus a12 y dot plus gamma 1 dot. Okay? And then I know what x dot is, because that's just x dot. And what is y dot? Well, y dot is just given by this equation over here. So then I can fill that out. And so what I get is x double dot is equal to a11 x dot plus a12 into a21x plus a21y. And then I can say, well, wait, I've just got y again, but I can take y from here. So I also know that y is equal to x dot minus a11x over a12. And so therefore, x double dot is equal to a11 x dot plus a12 a21x plus a21 x dot minus a11x. That's what the equation equals. So in other words, what I've got is x double dot plus x dot times minus a11 minus a21 plus x a11 a21 minus a12 a21 equals 0. And that is damped harmonic oscillator. So you're exactly right. So these equations are in disguise damped harmonic oscillators for x and y. Now, what I left out there was I didn't put in the noise. I just left out the noise. But if I'd put in the noise, then that noise would be on the right-hand side. Yeah. Okay, so that's neglecting the noise. So if we add the noise, put the noise back in and do the calculation I just did, just a little bit more carefully, then we have that gives terms on the right-hand side of the equation that are the forcing for the damped harmonic oscillators. And those noise terms are Gaussian processes whose correlators depend on B, and B, the matrix B, depends on the zeroth order solution. Okay, so, yep.
How do you do this in detail? Because you
I just
took
did it in
the
detail.
differentiation of the noise there, which shouldn't...
Yes. I'm not going to do it.
Okay, but is there a formal way
Yes,
to go around it?
yes. You can do it. Well, remember that we have Fourier transformed the noise. So gamma dot is just omega times the noise. Okay, and so you can write that down fully in terms of the correlators of the noise. Okay, but I don't want to do that. Okay, because I want to just move on from that. So this noise. So that's the first thing. There's the noise. The noise is white noise. And the coefficients in front of it depend on the solutions of the deterministic equation, the Lotka-Volterra equations. But they're still white noise. And because they're white noise, that means they have equal spectral weight in all frequencies. It's not colored noise, it's white noise. Okay, why does that matter? If I've got a damped harmonic oscillator, so this is something you learned on your mother's knees. If I have a damped harmonic oscillator and I excite it with a frequency that is just some defined frequency like this, it'll just respond in some particular way. If I excite it with all particular frequencies, with every single frequency, because that's what white noise is, the sum of every frequency, then there will be some component of the forcing that will hit the resonance of this simple harmonic oscillator. Every simple harmonic oscillator has a resonance. It has a resonance and it has a damping. Here is the damping, computed explicitly. So I'm exciting a damped harmonic oscillator with a stochastic noise that has equal spectral weight in every single frequency. So I will therefore be able to excite the resonance. So if I look then at the power spectrum as a function of omega, we can compute it exactly, but I'm not going to write down the formula because it's horrible, but it looks like this. Well, actually, it's not that horrible. Well, actually, I wrote it down already, so what am I talking about? It looks like this, and this thing over here, this is the resonant frequency of that harmonic oscillator. This is the shape of the power spectrum. Over here in the tails, it goes like omega to the minus 2, and you can see that because over here, well, there's a typo here. That's meant to be squared. Over here I have omega to the 4th on the bottom, and here I have omega squared on the top, and so it goes asymptotically for large omega, like omega to the minus 2. So basically, omega is the resonant frequency, and gamma is the damping. And so what this says is that any individual level model of discrete predator-prey objects will have modes that excite a resonance that is emergent from the description of the individual level model, and that mode, this frequency omega, will have a high Q factor and will be excited. And that is the reason why you have oscillations, because you're exciting a damped harmonic oscillator with white noise, and you're picking out the resonant frequency of the system. Now, this happens for every system. It's unavoidable. It's a consequence of being discrete, and it has a very interesting consequence. So if gamma happens to be small for some predator-prey system, because I haven't told you what the numbers are, if it happens to be small, then that means that the amplitude of the fluctuations will be large. And that can be true however large the population is. And the other thing that happens is if this is true, then what can happen is that the oscillations, the fluctuations can be so large that you can even get extinction. So let's draw a picture then of the phase space, and let me summarize what I've told you, what I've shown you. So summary. So point 1 is stochasticity intrinsic to discreteness drives population cycles even in the absence of environmental forcing or anything else. Two, this stochasticity is amplified by a resonance effect. And 3, stochasticity can lead to extinction. Actually, it's not that it can lead to extinction. It will lead to extinction. So let's have a look at the phase portrait. So let's have a look at what happens when I have the Lotka-Volterra equations with kappa equals infinity. So what I have then is these orbits, which we call centers. Right, I'm drawing in blue is no noise. When I add noise to this, what's going to happen is I'm going to be fluctuating around these closed orbits, like something like this, but I'm going to be diffusing off these orbits, and eventually I will hit here, or I may hit here. Either of those events then counts as an extinction. And it can happen either way. If I look at the Lotka-Volterra equations with carrying capacity being finite, so now what I have is fixed points with no noise. So I'd have a fixed point over here, but then with noise, what will happen is I'll be spiraling in, and then I will be spiraling out and going something like this, and then eventually I will hit over here, and then I will get extinction. And so there's a qualitatively different behavior when you have stochasticity and discreteness than when you have a deterministic problem. Just by being discrete, you're guaranteed to have extinction, you're guaranteed to have these resonances, you're guaranteed to have population cycles. So let me give you the references for what I've told you about. So reference 1 is a beautiful paper by Alan McCain and Tim Newman in PhysRev Letters 2005, I think. And then paper 2 is a paper by Irwin, by Reichenbach, Mobilia, and Irwin Frey. And that's in PhysRev E 2006. And then there's another paper by Parker and Kamenev in PhysRev E 2009. And what these papers do, these ones over here, they estimate how many cycles before you go to extinction. And you can calculate those things using scaling laws and various non-perturbative methods. And theoretical physicists find this all very interesting. But it's a fantastic aspect of this. So we've learned something that we did not know when we took a very naive view of what happens in a predator-prey system. Okay, so any questions about this before I go on to space? Yeah. Yeah, yeah. Yeah, you wait for the microphone, yeah.
So in the presence of, when you have like these environmental fluctuations, I would guess usually it has like a very narrow band of like modes that are being driven.
Well, I don't know. Why?
I don't know, but like when you have environmental fluctuations, what is dominating? Stochasticity or the environment, or does it?
I don't know. Depend? Tell me which environmental fluctuations you mean. I don't know. What's the power spectrum of environmental fluctuations?
Seasonal
it might be 1 over F noise. I don't know.
Okay.
I don't know about that. Maybe I don't want to ask an ecologist, but I don't know.
Okay.
So the point is, we've explained what you see with a minimal number of assumptions. Anything else you want to add to make this description more realistic or more complex, it still has to include these things, because these things qualitatively change the nature of the behavior. Okay? So if you want to look for where do the cycles come from, this is where they come from. I don't need any other external forces. I don't need anything else. Anything else I can do on top of that, yes, you can work it out. It's a well-defined problem. But the point is, this is what's really going on. Hey, hang on, it's coming.
I was just thinking, if you don't consider it to be white noise, you.
But we don't have that choice. We've proven it to be. Okay. We've calculated it. Okay. We didn't say, here's an equation, and I'm a physicist, so I like white noise, so I just add KT times white noise. We calculated it. Yeah. It all came in a systematic way from my master equation, which was an exact representation of the discreteness. Okay. Okay. And this is true. This is only in a limit. This is a limit where the noise is weak. Yeah. But even in that limit, we see this effect.
That's nice.
Okay. So it's very, very important. Okay. So.
Can I ask a question? Sorry.
Yeah. Sorry.
I was just wondering if you can keep going with the system size expansion for higher orders, because you mentioned that after second order you don't have the preservation of probability.
That's not true. That's true for the Kramers-Moyal expansion.
Okay.
Okay. It's not, so you definitely don't want negative probability and things like this. This expansion doesn't have that problem.
I see.
Okay. So you could go to higher orders. Yes. Okay. Although I've never done it.
But so you're not aware of problems where it's relevant to go to higher order?
Not that I know of.
Okay.
Not that I know of. Maybe Owen, do you? I haven't seen it either. Okay, so remember that we talked at the beginning. We said all this is weak noise. How do I know it's weak noise? Well, the expansion that we did was an expansion. I don't have the equations on the board, but we were doing an expansion in 1 over the square root of v, and the v was like the quote the volume. And I told you it's not really the volume of the system. It's not like the surface area of Earth. Okay. Wait. Can I finish this is what I'm saying before you ask me another question? So it's not the volume of it's not the area of the Earth or anything like that. It's a sort of correlation volume or correlation area that comes from the spatial structure. So to answer what that is, we're going to need to look at spatial structure. Okay, question.
Yeah. So I think this only makes sense if you know how to scale the rates with the volume, right? You have some rates that have
That's right.
the 1 over volume.
That's right.
And this is like
you have to
intuition-wise, or should be
no.
obvious?
No. You do it in a consistent way, and it is a tricky technical point, but it's not one that's in doubt. Let's not waste the class's time on esoterica. Okay, all right. So now I want to talk about space, because space is the final frontier. So now what I want to do is I want to do all of this, and we're going to do this for space. But if I just take the predator-prey model and then just add space to it, I can do a lot of calculations, and at the end of the day, it's not very interesting. Okay, I mean, you just get this, and you get some spatial fluctuations and things like that. But so I'm not going to do that. I'm going to introduce a new model. So we're going to do a stochastic Turing system. We're going to look at patterns when you have space, but it's not just a predator-prey system. It's a predator-prey system that has a Turing instability. And so what I want to do now is I want to review. Here are my goals. What I'm going to do is remind you of the physics of Turing pattern. And I firmly believe that if you're going to do physics, and particularly doing theoretical physics, if you don't understand something in cartoon pictures, you don't understand it. Okay? So I want to understand it without writing down any equations, just to understand what is actually literally going on. So I'm going to remind you of that, and maybe all of you here fully understand Turing patterns, and you don't need this. It's just some equations for you, but you fully understand it. But I know that when I first started thinking of them and working on this project, I didn't have the intuition about what Turing patterns really meant, and it was very helpful to me to think about what is actually going on. So I'm going to think about this at the level of cartoon pictures, and then I'm going to write down, and I'm going to actually look at a model of plankton in the ocean, which I think is one of the first Turing patterns in ecology that was ever written down. So I'm going to take a look at that model, and then what we're going to do is write down an individual level model of it. And then I'm going to calculate the phase diagram of that model. And then lastly, I want to make a prediction predict how to differentiate between stochastic and deterministic patterns. Okay, so that's what we want to do. So let's talk first of all about the intuition or cartoon picture of Turing patterns. So what we're going to do is we're going to have a predator-prey model, but with some extra pieces. So first of all, we're going to start off with predator-prey, but now we have space, and so that means that A and B can diffuse, and so we have diffusion coefficients dA and dB. So that's the first thing. So A is the predator, as usual. And now I'm going to use some language that comes from Turing literature. So I will call a predator, I'll call that an inhibitor. And we'll see why in a minute. And then B is going to be the prey, as usual, and we're going to call that an activator. So people who think about things like Turing patterns use that language. And we're going to assume, and this is in fact turns out to be essential, we're going to assume that dA is greater than dB. So that's an assumption. We're just doing a cartoon picture at the moment. We're not doing a calculation. Now, what we're going to demand of the activator, why is it called an activator? Well, it catalyzes its own production and the inhibitor. So this is the new thing. It catalyzes its own production. And then we have the inhibitor. And that reduces the concentration of the activator and itself. Like that. So unlike just the regular predator-prey, where the prey activate the predator and the predator eats the prey, here we have something different. The activator catalyzes its own production, not just that of the inhibitor. And the inhibitor reduces the concentration of the activator and of itself as well. All right? So you need both of these conditions. All of these things here, 1, 2, and 3, 1 plus 2 plus 3 are essential ingredients for the Turing pattern phenomena. Okay, so now let's draw some pictures of what we would think we would expect to see given this definition of what these variables actually do. Okay. So step 1. Let's start with random initial conditions. Okay, so here I'm going to draw, for example, B as a function of x. This is the prey. So I'm going to suppose I've got some random initial condition, but there's happens to be some peak at this point in space. So this is my picture at time t equals 0. So then what do I expect to happen? Well, if I look a little bit later, then what I will see is that this peak has grown more than the surrounding area. So this is t greater than 0 because of the fact that the activator catalyzes its own production and that of the inhibitor. So then I might say, well, that's fine. Now what happens? Well, if I now look later still, and again, I'm just plotting, for the moment, I'm just plotting B here. So I've got my pink curve, which I'll try to draw. Oh, that's the wrong color. I'm colorblind. Oh. Okay, so this is meant to be the same time as this thing here. So this is the same time, t equals t1. So this is t1. And then I'm going to ask what happens at a later time. Well, what's going to happen is that the prey is going to diffuse, and so this curve is going to now then sort of spread out something like this. So this is then prey diffusion. For times greater than that t1. Okay, well, if that's what the prey is doing, now let's have a look at what the predator is doing. So let's now put the predator on this graph. Well, the predator is now going to be activated by the prey, so the predator concentration will look something directionally like this. So now there is a large amount of predator which has been catalyzed by the presence of the prey. But now let's have a look at what happens a little bit later. Okay, so I'll try to draw these things in a consistent color. I'm not helped by the fact that I'm colorblind. So now what's happened is this. Now what's happened is that remember that the predator, this is A, has been let me finish this. The predator here has been catalyzed by the prey. And here, the predator is rapidly moving. And because it's rapidly moving, it stops the diffusion of the prey. But also, you have to remember that the predator inhibits itself and not just the prey. So the next thing that happens is that the predator starts to go down. So now what happens is the predator, so the prey is something now like this, and the predator is now something like that. So the predator inhibits itself, and because it inhibits itself, it doesn't overwhelm and kill all the prey. And so what you've ended up with as a result of this exercise is that you've found that what I now have is a local clumps, local spots of prey and predator. and that's how you form a Turing pattern. So that's the start of the Turing pattern process. It's a result of all of these, the interplay of all of these different effects, leaving you with some spots. So that's the cartoon picture of the Turing pattern. Okay, everybody agree with that? Yep. Was it news to anybody? Did anybody learn anything new for the last 2 minutes? Some people did, okay. All right, now I want to talk about this. Let's turn off the light a second. Is there an airport near here or something? Is what? I see. Okay. So this is the world, and what you're looking at here is a bloom of plankton in the North Atlantic, and you can see that it is very patchy and kind of random and stuff like that. So we would like to be able to understand how patterns like that form. Obviously, they form in a complicated interplay between biology and fluid mechanics effects like turbulence and the Gulf Stream and things like that. But basically, we would like to understand why the plankton are patchy. So here's a paper that was in Nature in 1976 by Simon Levin and Lee Siegel. I guess Simon was probably a graduate student or postdoc at that time. And it's not even a whole page of Nature, but it's a seminal example of the hypothesis of the origin of plankton patchiness as a Turing instability. Okay, so let's leave that up there, and let's go and describe what was the model that they proposed and why that model is perhaps not quite correct, but we can perhaps understand some of the features of it using stochasticity. So now we're going to talk about the Levin-Siegel model for plankton herbivore interactions. Okay, so so A is the plankton. No, A is not the plankton. A is the herbivore. So that is the predator. And B is the plankton, which is the prey. And so you might say, well, let's just write down the Lotka-Voltaire equations, but now we can add some diffusion. So you might say, okay, fine, so we have dA by dt is now the usual thing, PAB, and then I have some diffusion coefficient like that. So that's how you might start off. But then you might say, well, I also have the predators can die out, but it's worse than that. The predators are the inhibitor, and they reduce the concentration of the activator and themselves. So that means that they act catalytically on their own death, and so that means that they have to be described by a term that goes like A squared. So this is describing predator competition. And then I can write down an equation for B. So that's going to just diffuse like we've seen before. I have the birth of the prey. I also have the predation by the predator, but we also have the fact that the prey unlike the regular Lotka-Volterra, the prey are the activator, and the activator catalyze their own production as well as that of the inhibitor. So what that means is that the term that comes in here is a term that you haven't seen before. It looks like this, EB squared. And this thing has a name for ecologists. This is known as the Lee effect. And what the Lee effect tells you is that if you're at high density, you have a higher rate of reproduction. Or the corollary of that is that if you're at a low density, you have a lower rate of reproduction. Anybody who's, well, never mind. I was going to make a joke, but I think I won't. Okay, so you can. So the steady state of coexistence, it's quite easy to show, is when P is greater than E and P squared is greater than DE. And then you can work out what are the conditions for coexistence. So what you get is B star is BD over P squared minus DE, and A star is equal to BP over P squared minus DE. So that's all something very simple that you can just calculate by looking at the steady states of these equations. And then the next thing you can do is you can look at the linear stability analysis, and you can ask, when can I get a pattern? And the condition, I'm not going to do the calculation for you, the algebra, but I'll just tell you the result. So what is the condition for an instability of the uniform state? And that is equal to this. dA over dB is greater than P over D square root minus the square root of P over D minus E over P, and then this whole thing raised to the power minus 2. Okay, so that's the condition for there to be an instability. And let's suppose I choose my reaction terms to be of order unity. So let's say B is equal to half, C is equal to half, D is equal to 1/2, P is equal to 1. Then if I compute that, then what it says is that dA over dB has to be greater than something about 28, a very large number. So it says that I only get a Turing pattern, Turing instability, when the inhibitor disperses vastly more than the activator. And usually if these things are sort of chemical molecules, or molecules just floating around, or they're organisms in an environment, their diffusion coefficients are, they may be different, but they're not going to be different by a factor of 20. And so this is regarded and is generally unrealistic. And that's why we don't see Turing patterns. Hard to see. Okay. So now you might say, well, that's too bad for Turing, but everybody really likes this idea of the reaction diffusion and instability that gives rise to a Turing pattern. So it's sort of like hard to believe that it just doesn't work. And but in fact, we can save it. We can save it by stochasticity. So let me tell you what is the bottom line here before I go into any calculations. So the bottom line is that you might ask the question, does stochasticity unexpectedly stabilize patterns just like it did for predator-prey? So what we found with predator-prey was we couldn't understand why there was population cycles, and we discovered that the most unlikely effect in the world, randomness, actually stabilized population cycles with a well-defined period. That was a very surprising, intuitively not obvious at all idea. So you might say, well, maybe that works in space as well. Will stochasticity somehow stabilize the patterns just like it did for predator-prey? And why might you think that? Well, when we talk about a Turing instability, when you go and do a calculation of a Turing pattern, as some of you have done with realistic models, the pattern that you're looking at is a periodic pattern. But I didn't say I was looking for periodic patterns. I just wanted to look at patterns. Okay? So maybe it could happen. Maybe stochasticity, through some resonance mechanism, could stabilize the pattern, but that pattern might not be the same pattern that you're used to. That pattern might be a random pattern rather than a periodic pattern. So the answer is yes, it does. And the pattern is not regular, but has a well-defined characteristic scale. So you say, well, I've got a Turing pattern, it's got a well-defined scale, all the patterns are in some periodic array, everything looks nice and beautiful when I plot it out and publish it in the journal, but I can make a pattern that's not regular that still has a well-defined characteristic scale. So what we're going to see is that, in fact, stochasticity, through a mechanism very similar to what you've seen already, does indeed stabilize the pattern. And it does it, the patterns that you get are not regular. They have a well-defined characteristic scale. And they have a well-defined characteristic scale and correlation function. And tomorrow I'll show you the results of an experiment that we did to test the theory. Okay, so that's the bottom line. So now what I want to do is I want to show you at least some idea of how we do the calculation, because it is technically quite involved, and to do it right, it would take me far longer than just 1 or 2 lectures. It would take a couple of weeks to really make sure that everybody understood all the field theory and everything like that. And so what I'm going to do is show you some very simple shortcuts, and also just some of the ideas that come into how theorists work out this very difficult spatially extended stochastic problem. So let's make another comment then about why this is difficult. So this is a really hard problem. If you go and look at my papers on this, they are pretty impenetrable. I spent the morning just checking the algebra and going through them. They're fairly messy. Now, why is this problem hard? Well, if we look at the predator-prey problem that we just did with no space, so that's essentially zero-dimensional. Right? We just had a well-mixed system, so it's just one variable and a pointer, the A variable and the B variable, just fluctuating in time. And we had to write down some master equation for the number of A's and the number of B's and time, and then we had to do all this fancy Van Kampen expansion and blah, blah, blah. Okay? Now suppose I have a spatially extended system, spatially extended predator-prey, and spatially extended Turing. Okay, the reason I didn't show you this, the spatially extended predator-prey, because I really don't want to do all this work and in the end have a result that's not very exciting. Okay, but what's exciting here is that with the Turing patterns, you do get something that's worth phoning home about. Okay, why is this hard? Well, then you've got a spatially extended thing. This was true at a zero-dimensional point. So what that would say is that if we're going to use the same formalism, we would need to have a probability distribution for the number of predators, the number of prey at the point R and at the time t. So I'd need to do this. I'd need to have an infinite number of master equations, one for every point in space. Okay, and that's awful. Okay, people tried to do things like that in the early days of quantum mechanics, and they gave up, and then they invented a framework called quantum field theory that enabled you to deal with that. And so actually, in the end, we use quantum field theory to do these calculations. If we didn't know quantum field theory, we wouldn't have been able to do this work. Okay, so that's the first thing. Okay, so the next thing I want to do, I'm conscious of the time here. I'm going to try to stop in about 10 minutes. I'm conscious of the time here. The first thing I want to show you, I'm not going to go and derive things. I'm just going to show you the results. So I want to tell you about the effect of external noise on a Turing pattern. So I want to do this for two reasons. So I'm now looking at the effect of external noise. Up to now, I've been emphasizing that all the noise here is intrinsic in the particle discreteness. So why am I suddenly looking at the effect of external noise? Well, I'm doing this for two reasons. Reason number one is later on, I want to differentiate between intrinsic demographic stochasticity and an external noise. So I want to know what is the answer for external noise. So that's reason number one. Reason number two is a bit more subtle. Remember when we did the Van Kampen expansion just for the regular predator-prey system? When we did that for the regular predator-prey system, we ended up with an equation for the fluctuations, which was a Langevin equation, and on the right-hand side was a noise that we had derived, and we derived its forcing, and we derived what its behavior was. And that noise involved the previous order in perturbation theory, in other words, the solutions of the mean field equations. So the fluctuations were in fact driven by the solutions of the mean field equations. This was what is multiplicative noise. But from that point of view, that says that if I know what the formula looks like for external noise and the way I know how to treat that, then I can kind of do a shortcut and say, well, in that case, I can just put it as the external noise, the source of it being the order from the previous perturbation theory. I'm not going to do a shortcut like that, but you can see that that would be the logic. So let me just tell you what the answer is. So what do you do? So what you do is you linearize about the Turing fixed point, about the Turing steady state. You write down a Langevin equation, because you don't have to do Van Kampen expansion or anything like that. You just have to write down a Langevin equation, so you can do that. You've got external noise. And what you find is that my minus I omega x is equal to A times x plus some gamma. And what do I mean here? So x is the vector A minus the steady state the predator, and B minus the steady state. So it's that vector. And then A and B are some matrices. Well, actually, there isn't a B yet. A is some matrix that depends on A star and B star. Doesn't really matter. It's in the notes. You don't need to know precisely what it is. And the noise has a correlator which is now extrinsic. So this is just some number sigma squared that you give me times delta r minus r prime, delta of t minus t prime. So that's the setup of the problem. So once I've got this Langevin equation, I can then easily compute the power spectrum. So I've got x of omega, x of minus omega, calculate that. So I just take this equation, multiply it by its complex conjugate, do the average over the probability distribution of the noise, and what you end up with is a formula for the power spectrum. And I'll draw that, or at least I'll tell you what it looks like, and then we'll move on. Okay, so then if I compute this, I get P of k and omega. It's a power spectrum now in wave number and in frequency. So it looks like the fluctuation in k and omega squared like that. And it's some god-awful mess. So it's mess number 1 over mess number 2. And that mess involves things like sigma squared, A star, B star, K, E, B, P, etc. Everything you could think of. And the main thing about this is that this is of order omega to the 4th, k, or k to the 4th on the top, and on the bottom it's divided by something that is of order omega to the 8th or k to the 8th, plus all sorts of terms on the bottom. And so what that says is that if I then were to look at what happens as I take k to infinity, omega to infinity, then this thing goes like omega to the minus 4 or k to the minus 4. So the power spectrum has a very particular shape, and we can then go ahead and calculate that. The other thing that comes out of this calculation that I want to mention before I finish is that what is the condition for a Turing pattern in this case? And again, you can calculate that. It's not that hard. And what you find is that its EDA is greater than PDB. So over here on the other side of the board, we have a very difficult to satisfy condition for the deterministic Turing pattern. When I drive it extrinsically, we see that now the condition for the Turing pattern is this thing, which is a mild condition, much better than before. So that already might give you some hope that the addition of noise might make a Turing pattern easier to see. On the other hand, it already suggests to you that the Turing pattern will be a disordered pattern. Okay, so I think I'm going to stop here at 3:30. This is when I'm supposed to stop, right? Yep, I'll stop here. I will continue tomorrow with the outline of how one does the calculation. And then talk about the applications of this, not just to plankton, but to signaling molecules in a biofilm and to waves in the brain, in the visual cortex. Okay.
Questions? So what would be the nature of this external noise? For example, in the plankton scenario, would be like interactions with species that are not involved in the model, or something?
Something that's not involved in the model. So I'm just exciting the system with some changing the concentration of some chemical or something like that.
But is there like a strong argument for non-multiplicative noise?
Is there a strong argument for?
For additive noise, because it doesn't depend on the abundances. Right?
No, but you might say, here's a situation, I'm going to manufacture this in some microfluidics device or something like this. So you can imagine somebody doing it in a computer or doing it in a laboratory, or you might say, I've got a Turing pattern, which is the plankton in the ocean, and it's being forced by the day-night oscillations, it's being forced by seasonal oscillations, it's being forced by ocean currents. So you can think of many periodic external drivers that could be doing this. And they could be correlated in space, they could be uncorrelated in space. So it's certainly something that you can consider. If we're going to try to understand what happens, this is probably the easiest calculation that one can do to at least be able to see roughly the structure of what's happening. And it's already told us something interesting, okay, with virtually no work. Okay, did I answer your question? Johan? Or is there somebody over on the side of the room? No,
yeah,
go ahead.
Students first. Students first. Any students?
No, they're still asleep.
So
Yeah. So I wanted to ask you if this effect can be related to stochastic resonance.
No. This whole mechanism, you remember I told you about the stochastic, and I told you there was a resonance. This is not the same thing as stochastic resonance. Okay, but let's not waste time. We won't talk about what stochastic resonance is and why this isn't like it. But it isn't. It isn't the same thing at all. But thanks for the question.
So could you, instead of working in continuous space, work on a lattice and then expand? Like try to approximate space with a lattice and then go the lattice size to 0, something like that. Would that give you a more reasonable way to repeat the formalism?
So my approach to life is that I can either do this if my ear is itching, or I can do this, and I prefer to do this. So yes, you could do that, and you might even say that if you're going to sort of really work out the field theory formalism properly, as I've emphasized in my earlier lectures, to define what path integration means and things like this, I've got to worry about the discretization, I've got to worry about the regulation, and so on and so forth. All of those issues are absolutely important mathematical issues that you have to get right. I wouldn't say that they make things easier. I'm trying to find the sloppiest, easiest, and quickest and most convincing way to show you what is going on without being rigorous. But so I don't think it offers any particular advantage. I mean, the reason that theoretical physicists like using continuous fields, functional integrals, functional differentials, and so on, is they like to fool themselves that they think they understand what is happening in strongly fluctuating, spatially extended systems, and they can use something like the rules of calculus or functional calculus. In reality, you can't. In reality, as soon as I put a noise which is non-differentiable onto a partial differential equation with derivatives, none of it makes any mathematical sense whatsoever. And so then you have to start worrying about regularization and Bessel spaces and Sobolev spaces and all sorts of things like that. And so it doesn't help in terms of doing what a physicist wants to achieve. But it is important to do, but it's very difficult. Martin Hare won the Fields Medal for being able to do that for just the simplest, interesting non-equilibrium stochastic equation, the KPZ equation. That's how hard it is to do that kind of thing. Okay, thanks for the question there.
Yeah.
I think Johan, you have a comment on my answer.
Comment your answer.
Yeah, yes, please, yes.
When you do this, so when you go on a lattice, you don't really gain much. What you gain is you recover the demographic noise that Nigel is deriving, which you get from the well-mixed. And then on top of it, you get the stochastic contribution from the Brownian motion noise, but that's subleading, so you're wasting your time.
Yeah. On top of all the other objections I made. Johan, yes.
Yeah, I was a bit puzzled by your remarks on the far away screen, because I quickly looked it up, of course. And so a basket shark goes at about 1 meter per second. A whale goes even faster.
What is about a meter per second?
A basket shark. It's a marine predator of plankton. Goes at about a meter per second. A whale goes even faster. The krill goes at between a millimeter and a centimeter per second. That's a factor 1,000 to 100 difference.
You're totally
so that thing there is too small.
That's right. You're right. You're right. You're absolutely right.
And then you might remember these.
But you're right. But you're right. You're right. But we're talking about the diffusion coefficients and not their ballistic velocity.
Yeah, I'm worried about that also.
Yeah. So in the context of this model, and of course you might say, look, if I'm looking at marine plankton and herbivores, are they really doing diffusion? Are they doing advection diffusion? Is there convection going on? Is there advection from currents and so on? Yeah. Absolutely. All of this has to be redone in a more realistic setting. When Simon and Lee Siegel were proposing this, they were just saying, let's just make this simple as possible. So that's what those numbers are. So not the velocity. You're totally right.
I wanted to add to if you know how for instance, these humpback whales hunt, they make a little screen of bubbles around a patch of plankton. So the plankton is patchy.
Yeah.
So there's lots of things going. I think actually the model is made simple for the situation.
I fully agree with you. I don't think Simon would for 1 minute say that this model is the most realistic model in terms of marine animal behavior. Just putting out there is here's a minimal model of Turing pattern formation in an ecological context. I don't know if there were earlier ones. You might know that. I don't. But this is the model that we're looking at. It's what?
It's a classic.
It's what?
It's a classic.
It's a classic, exactly. It's a classic. And so it's like, if you can't solve this one, which is certainly simpler than what happens in real life, for all the reasons that you said, with whales blowing bubbles and things like this, then you may as well go home. So we're just trying to even understand this. And remember, I'm a theoretical physicist doing this, so I'm not trying to predict what next year's krill harvest is going to be in the mid-Atlantic Ocean. I just want to understand what the heck is going on so I can at least have a well-defined theoretical framework by which I can understand at least the processes that are going on and make some predictive models.
Sure.
I mean, that's what you do too. Right?
True.
The Turing patterns that you're talking about are also ignore all sorts of effects.
Well, but you're saying that the Turing patterns are not there, but they are there.
No. They are there, but those diffusion coefficients, those are diffusion coefficients, not velocities. They're different.
Yeah, but are they so? Well,
one is a coefficient of how distance scales with the square root of time, and one is the coefficient of how the distance scales with time. They're very different numbers, and the number that comes in here is just the diffusion. We're not just. So
I tried to look that up also, and I couldn't manage to.
I don't know, but anyway, that's why it's been hard even to make Turing patterns in the laboratory, let alone in the ocean. Every time somebody in a chemistry department succeeds in making a system that has a Turing pattern, they can really prove it's a Turing pattern. That gets into the national newspapers. It's so rare. Okay, I should go on to somebody else's question.
Talk about it.
Yeah, of course. Yeah.
Anyone else has any other question?
Yeah, but
Fan has a question up there.
Just to check my understanding, so this formalism should be straightforward to generalize to more component than two species?
This should be straightforward to generalize to what?
To more components, like more species than just two.
Oh, yes, it should. Can you do two? Okay, so let me teach you how to do two, and then you can do 3, 4, 5, 6, 7, 8, 9, 10. I see that there's a series there. So even to do two is really hard. Okay, it took us ages to do these calculations. Well, maybe you'd be able to do them quicker. I don't know.
Wonderful, Nigel. I have a question. You started out with the heuristic picture.
Yeah.
And you emphasized that the on itself is very important.
Yes.
And that includes the term dA squared.
Correct.
When I see your final condition, there's no d. So
there isn't.
Yeah, so that puzzles me.
Actually, it puzzles me too. I don't know what it means. I don't remember why it turns out to be like this or what it means. I don't know the answer to your question. I don't remember if this is the. I mean, I think this is the necessary and sufficient condition for there to be an instability. It doesn't mean that the wavelength of the instability doesn't involve all of these things. Okay, so this is just in the same way that here, this is just that if this condition is not satisfied, you can't have an instability. And then you can say, okay, let's suppose this condition is satisfied, then what is the wavelength of the instability and so on? That's a separate question. So there's a condition which is, does this thing ever happen at all? What is the necessary and sufficient condition for it to happen? So that's what that is. That's why not all the parameters are in that condition. And as far as I remember, well, I have to check, but I think that's what the condition is, but I didn't review it carefully before I wrote it down. Did I answer your question?
Yeah.
Okay, thanks.
So I think we can stop here. So we have some time for the coffee break, and then we resume at 4 for the roundtable. And also remember that today at 7:30 we have the dinner in the place that you got by email. Okay.
So show me the round table.
Sorry?
Show me the round table.
I think it's good. It's fine if we just do a line table, linear table.
It's a one-dimensional round table.
I see. So it's a firing squad.
Okay, let's thank Nigel for the talk.